Today, I will be talking about the process and results of my project based on the NP-complete numerical three-dimensional matching problem done by myself, Pete Miglio. First of all, what is a numerical three-dimensional matching problem? It can best be described as there being three sets of integers. Each set is of the same size, k. A value called the bound is given. There is a solution where the shuffled sets produce k subsets, where each subset has three integers, one from each set. There is a solution where the shuffled sets result in k subsets, where the sum of all integers in each subset is equal to the bound. This may sound hard to visualize, so here is an example. In this example, given three sets x, y, and z, and given a bound of 10, find the solution where all subsets sum to 10. If we look at the first value in each set, which are 1, 3, and 2, that would be a subset. This subset sums to 6. 1 plus 3 is 4, and 4 plus 2 is 6. But 6 is not equal to the bound, so this would be an incorrect match. There is a solution where if the sets are shuffled correctly, all subsets sum to the bound, this solution being 1, 7, 2, 3, 3, 4, and 5, 2, 3. All three of those are subsets, which can be made using the three sets given. And they all sum to 10, which is the bound. In the code for my project, and throughout this presentation, I use the terms set, subset, and solution when talking about the solutions. A set is shown in blue as one of the three integer arrays. A subset is shown in red, and it only holds three integers each time and every time. A solution is a set of three sets. The solution is the same solutions that will be bred throughout the genetic algorithm. It is shown in green. In my genetic algorithm, I have three stages for each generation: a crossover stage, a mutation stage, and a cleanup stage. The genetic algorithm is done 10,000 generations, which is 10,000 times, and each time a crossover, mutation, and population cleanup is implemented. First, the crossover is done by taking two parent solutions. The first half of the parent is taken and given to a child solution, and then the second parent fills in whatever the child solution doesn't have. So you can see in the picture here, in parent solution, in step 1, the first half of the parent solution's numbers are taken, 5, 2, 3, 6, 1, and then the parent solution 2 gives whatever the child solution does not have already. Mutation is next. Mutation is done by generating a random decimal number between 0 and 1. This random number I call the chance. If the chance is less than or equal to the mutation rate, which is given and set in the code, if it is less than or equal to the mutation rate, a value gets swapped with its neighbor. You can see in the picture here that 10 and 9 would become 9 and then 10. And this occurs for each value in each of the three sets in any given solution. So in each set, every integer is given a chance to mutate, and a random number, called the chance, is determined for each and every integer in each and every set. Lastly, the population cleanup is done by taking the solution with the fewest sums matching bounds and removing it. So the solution with the smallest amount of sum matches that are equal to the bound is taken away so that the population has sums that are bigger in number. That way the population stays at a regular number. During the wisdom of crowds phase, the top 25% of the population is taken. The top 25% is defined as having the most sums that match the bound. First, the solution with the highest bound match count is looked at, and its subsets are taken. Next, every other solution in the top 25% is looked at, and their subsets are taken, assuming that the subset doesn't include values already given to the final solution. Finally, the final solution is filled in using a greedy algorithm matching values to make sums equal to the bound until every set is filled in the final solution. Looking at the average amount of matches per solution on a population per generation and using genetic algorithm, you can see from the first image the average value hits a spot and stagnates. This is because the mutation rate is too weak and the number of integers in each set is too low. If the mutation rate or number of integers is brought up, the opposite of stagnation occurs, which happens in all the other three images in this slide. But then there's more variance and less consistency. And also, in each of these pictures, the average value ends up being around a fifth of the size of the set. We want it to be the whole size of the set. The size of the set being k. So in the first image, k would equal 10, and the average value ends up being around about 2 or 3, and that's about a fifth of k. And the same goes for each picture in this slide. The same can be said about each of the images in this slide as well. This slide shows the total sum of match count per generation, which means the sum of all bound matches in a population. So it should show a similar story between the slide before it and this one. Again, the average sum found is about a fifth of k. In the charts here, I compare the best final results from many tests of just genetic algorithm versus results of genetic algorithm in addition to wisdom of crowds. The results show that wisdom of crowds is better than only genetic algorithm because it brings more sum matches. You can see in the gray lines for each picture in the slide represents the wisdom of crowd matches. and every time the wisdom of crowd matches on average are higher than just the genetic algorithm matches. But still, the wisdom of crowds only brings the number of matches to about a quarter of the size of the sets, instead of just a fifth of the size. Because of these results, I conclude that this method of genetic algorithm in wisdom of crowds is insufficient. A balance between number of integers and mutation rate needs to be found. The greedy algorithm in the wisdom of crowds portion works only partially because there are 3 sets to match and not 2. The greedy algorithm in the wisdom of crowds portion finds 2 random numbers in 2 of the sets and then tries to match it with the third one. If it was just 2 sets, it would be easier to match. And lastly, although the algorithm overall finds on average a quarter of bound matches, and even though it is lackluster, it is on its way to finding all bound matches. There is little research I could find about the numerical 3-dimensional matching problem, so hopefully this is progress into solving it.